The floor is yours.
Okay, thank you very much. And thank you for organizing this event in these difficult circumstances. I can imagine it's not easy. So I'll present my chair that's called AIGRETTE, and a little bit like Gilles Blanchard's, my acronym is kind of a bit tortured. So it's Analyzing Large-Scale Geometric Data Collections. And just before I start, I want to mention a couple of words about my own background. So my background is primarily in applied mathematics and in computer science, and since 2012, I've been a maître de conférence at École polytechnique in the LIX lab, and since 2008, a professor there. And I'm part of the, so I'm embedded within the Laboratoire informatique de l'École polytechnique, and we have a group dedicated to visual computing that's called GeoVic. And in this group, there are 4 other permanent researchers. This group is headed by Damien Romer, and we have other colleagues like Marie-Paul Cany, Pram Memory, and someone who's just joining, Vicky Collegaten. And we have many kind of ongoing international and local collaborations. And I'm personally supervising 5 students and a postdoc. And of course, if there's any interest for collaboration, this is, I think, one of the ideas behind this kickoff meeting, and I'd be very happy to extend our network or welcome new members. So I'm also a little bit lucky, I think, because Fred Chazal's talk set the context for my chair very, very well. And basically, the general motivation is that we have a lot of geometric data nowadays. And Fred's presentation was dedicated to more higher dimensional or temporal data. I'm maybe in some ways a little bit more or less ambitious, and so I'm mostly focusing on 3D data with a little bit of kind of outlook to higher dimensions as well, but mostly for data in 3D. But even in 3D, we have a lot of interesting data sources coming from computer-aided design, computer animation, biomedical and cultural heritage imaging. So basically, nowadays, acquiring a 3D shape, for example, with a 3D scanner, is getting easier and easier. And so there's a kind of a deluge of geometric data that's happening. And unfortunately, this geometric data comes in many forms and many representations. And many of these representations are not very well suited to modern learning applications. So for instance, often we have data that comes in a form of point clouds. It's just a collection of 3D points. We have triangle or quad meshes, which is a common in computer animation, for example. And also we have even graphs, when you're dealing with interactions, for instance. And the general vision that I have, both for this chair, but also kind of more globally in my research, is to try to abstract away from these different representations and to present a kind of a unified computational framework for basically analyzing this data regardless of the different kinds of representations. And one of the things that I've been really exploiting is basically finding relations or correspondences that might exist in different data representations. And kind of one thing that's a little bit too bad is that this data processing has evolved in different fields independently. And so, for instance, there's computer vision and computer graphics, and often they don't communicate very well. And so we basically try to bridge these gaps together. Another big kind of motivation specifically for this chair is that, if you look at what's happening in computer vision, so analyzing 2D images and all the tremendous progress that has been done over the past, let's say several decades, but especially in the past 8 years or so, there are 2 big components that are very important. First of all, there's a lot of label training data. So many of you would be familiar, for example, with ImageNet, which is a very large-scale effort for collecting and labeling natural images. So they have tens of millions of images labeled. And the other big component is that typically, so still, despite many years and a lot of effort, the main building block for the most successful architectures for analyzing, for example, image classification are convolutional neural networks. So these rely on the fact that basically an image can be represented with a fixed matrix, fixed grid of values. And in the case of geometric data, so when you're dealing with 3D data, for instance, unfortunately, these typically don't apply, right? So we have basically the main challenges are that, so we have some amount of data, but it's nowhere near the scale that exists in computer vision. So maybe we have thousands or tens of thousands of 3D shapes compared to millions of images or even billions of images for large companies. Another big challenge is that geometric data is typically unstructured. So, for example, you have just unordered collections of points in 3D. And so typically convolutional neural networks don't apply, at least directly. So there's some effort of applying convolutional neural networks with voxels, so basically extending them directly in 3D, but that typically doesn't work as well. And so there are lots of kind of challenges related to that. And another challenge, as I mentioned, is that our data often comes in different representations. And also what's very important is that it's riddled with noise, outliers, acquisition errors, etc. So, 3D acquisition is nowhere near as accurate as 2D acquisition. And so whenever you're dealing with, this kind of data, and I think this is something that we've heard in a few other presentations already, this notion of robustness has become very important because especially, in this kind of acquired data, you have lots of noise. You have to deal with this. So basically existing large-scale data sets, maybe have tens of thousands of 3D models, if you're lucky, but we also have, data coming from partners. So for example, I worked a little bit with people from the Natural History Museum, and they have maybe tens or hundreds of instances in the best case, or maybe in some biological acquisition you have thousands of instances, and that takes years of effort to acquire. So basically, the main objective of my chair is to try to develop algorithms that would kind of answer these challenges. And so what we're trying to hope to achieve is first develop efficient algorithms and mathematical tools for analyzing diverse and heterogeneous geometric data collections. And so I put kind of emphasis on the fact that it's geometric because I think there is a little bit of opportunity that hasn't been exploited yet. And namely, because we know that this data has this geometric flavor, we could maybe hope to address some of these issues coming from the fact that we have very little labeled data. So basically, kind of specifically what I hope to achieve is first study different representations that would be suitable for modern learning pipelines and, try to basically extend beyond like point clouds and triangle meshes and kind of have more or less unified frameworks. And kind of very specific to this effort is trying to inject geometric prior information. So since we know that these are 3D shapes and typically they're actual physical 3D shapes, so one of the hopes is to basically inject some geometric prior information into the learning pipeline. So both to develop tools that can extract some low-level features like normals or curvature, or maybe even exploit some topological features, as Fred mentioned. And also another big thing that I have, I think that could be useful, and we've been working on a lot, is to basically try to introduce consistency measures across individual objects. So this is, a somewhat common approach in computer vision. So there are these kind of cyclic constraints that have been used, for example, in GANs, but I still think that especially in geometric data, this can be used much more. And of course, hope to develop robust methods capable of handling noise and artifacts. So these are kind of high-level axes of study, and I won't go into like the technical details of each, but maybe just briefly, I wanted to mention a couple of ongoing or recent projects that we have done in these directions. So first is basically a method that is very simple, but this turns out to be quite useful, that we call point cleannet. Is basically a method for denoising dense point clouds. So, given a point cloud maybe with hundreds of thousands of points or millions of points, we'd like to basically remove outliers and denoise it. So basically extract some clean surface underlying this object. So this is a work that we did with some colleagues at UCL and a PhD student of mine. And basically this is a supervised learning framework, but the main interest is that, we can do this at scale, scale being the number of points, of course. Another recent work is on shape correspondence or non-rigid shape matching, where the idea is, given two 3D shapes, maybe represented as point clouds or meshes, how do we find dense correspondences? So basically a mapping between points on one surface to another surface. And, we extended a large number of techniques from the past and did also a large scale comparison and proposed basically a very robust method that can work directly on point clouds. That combines basically two main things. One is a feature extractor, and another one is basically a spectral representation of shape correspondences. And finally, we've also worked, and I think there's quite a lot of opportunity here on how to define convolutions and work directly on non-rigid 3D surfaces for different kinds of tasks. So typically you assume that you have a shape that's embedded in some larger space, but you can also try to define convolution directly on the surface. And, in some cases you might get away with less training data, for example, because you already encode some amount of invariance. So we've also worked in this direction, especially with my student, Adrian Polinar, who just graduated. So yeah, that's basically all I wanted to present. Thank you.
Thanks a lot. That's great. So we have plenty of time for questions. Yes, Bertrand?
So I guess all this is super expensive in terms of computation. And so you probably need to have very efficient libraries for that. So could you tell us about the strategy to have good libraries to be able to benchmark methods, etc.? So are you designing such a library within the...
That's a great question, and I agree that this is a big issue right now. So essentially what we're doing, and this is something that has, I guess, been gaining momentum, and it's a small step, but it's an important step, is that basically all the code is now released. So basically every paper, kind of in this area now shares the code, so it becomes much easier to compare against. So at least for recent papers, it's become much easier to do evaluations. So you don't have to implement everything yourself. And of course, you have major libraries like PyTorch or TensorFlow that relatively make it easier to do comparison. But it's still kind of a big issue because there are lots of versioning problems, there are data format issues. So I agree that it would, we can do much better basically than what we have now. And another thing that I think you also asked is how do we deal with computational complexity? And yeah, this is part of the chair. Basically, we hope to, right now, so far, we've been mostly working with our little resources, with whatever GPUs we can acquire, and setting up little server stations. But I hope also to basically extend to a bit larger cluster and try to get better computational resources. I feel this is going to be an issue for many of these chairs. From the description that I've seen so far. So if there's a unified effort, that would be even better. But I guess that's something we all have to deal with.
Yes, definitely. The infrastructure might be part of the package, or at the level of the DATAIA or the IPP, whatever. I had another technical question. You were saying, if I follow, that the one of the main problems is the noise, but some of the papers or the directions you were mentioning about the equivariance network, this is the idea that you could say actually deal with a collection of points as if it were a distribution. So would that solve the problem of noise?
That's a good question. I'm not completely sure I fully understood it, but maybe I can answer in the way that I did understand. So the problem of equivariance, so for instance, we worked on equivariant networks for surface convolution. So there, the problem of equivariance was a little bit different, and it wasn't so much with noise, but more with the fact that basically on a surface you don't have a consistent coordinate system, right? So in 2D you have the x and y coordinates, but in on the surface, there's basically no canonical coordinate system. So we try to basically answer that problem by designing a network that is equivariant to the choice of the local coordinate system at every point. But I think your suggestion is very interesting in the sense that basically maybe we can, it's a little bit different, and it has to do more with noise, and basically, you know, if we can kind of model the way that the noise is created and maybe design a network that would be by, you know, kind of by nature equivariant to this noise source, maybe that could solve some of our issues. I don't think there's a uniform, like, honestly, I don't think there's a single answer to the issue of noise in data, I mean, 2D data or 3D data. So basically any step is useful. One thing that I mean, maybe I can mention, for example, in this work, it's very difficult to model real noise because basically you can construct some theoretical model for what noise looks like or what outliers look like. But very often when you deal with real data that actually comes from 3D scanners, that noise has different properties. And it's, I mean, of course, like modeling is very useful for, you know, having robustness guarantees and, you know, basically maybe some theoretical things you could say, but it's very difficult to kind of make that jump from modeled synthetic noise to real noise. And so there are some techniques that allow you to simulate realistic noise. So there's even software that does this for 3D shapes, like that simulates noise coming from real scanners. But every scanner is a little bit different. And I can't imagine that it would be easy to have an explicit model that then you can design an equivariant network to. It might be possible, and I think that's definitely an interesting direction. Okay. But yeah.
Okay, so yes, it might be a very interesting direction. Typically, the way people are, I mean, Maron and the others, the way they are trying to find how you can define a group of, say, a group of, for instance, permutation is one, but you might have also various invariance operators on your data, and you want, say, your network to be indifferent to this group of invariance operators, so it might be interesting.
Yes, I'm familiar with some of that work, and I think it's fascinating, and especially from the fact that, so I think there's definitely a lot more to be done in that direction. Yes, thank you.
I completely agree. So I don't know, perhaps Bertrand is willing to install, and then we'll have another question. Is there another question? Okay, so I have one. You were saying about the geometric prior. What do you have in mind?
Well, it really depends on the application. So maybe I just very briefly mention one. So for instance, you know, this is a problem that I worked on a lot, which is shape matching or shape correspondence. And basically the problem is, given a pair of shapes, you want to find a dense, you know, point-to-point assignment. Yes. And now you can formulate this problem in many different ways. Yes. One of the ways that it has been formulated is just basically a classification problem. So for every point, you can say, okay, what is the right class according to some given set of point categories? Mm-hmm. But that kind of completely ignores the fact that, for example, a correspondence naturally should be continuous or smooth, or maybe it should even preserve some, you know, quantities like curvature or pairwise distances. And so this is the kind of information that you can often inject without sacrificing too much, you know, of the expressive power of the network. And it has really been useful, especially when you don't have too much training data.
Yes. Yes. Okay. Well.
Okay.
Thank you.
Okay. Thank you.
Thanks a lot.